This is a SIA A21 January 2014 questions in thermal physics. So they love to give you a question involving a graph and how you can link that graph to a equation. So this here is showing a graph of pressure against the mean square speed of a fixed mass of carbon dioxide molecules trapped inside a 50 centimeters cubed container of fixed volume. So here I have my volume. Okay, now the first part is write down an equation for the gradient in terms of n the number of molecules, m the mass of one molecule, and v the gas volume. So looking at the graph, we have pressure and c squared. So you have to think of all those quantities that you have. So pressure, mean square speed, volume, number of molecules, and the mass of one molecule, and what equation links them. So the equation is PV is equal to a third NMC squared. But to make it look like this, like the graph, we have to rearrange this equation to have P on the y-axis and c squared on the x-axis. So in order to do that, we have to rearrange this to look equals y is equal to mx. So because the equation has to equal to p, we have to get rid of the v by dividing it. We'll do that both sides. So p is equal to a third nmc squared divided by v. So here we have our y. So on our y-axis. On our x-axis we have c squared. So that means that everything in front of this is our gradient. So from this equation, our gradient is a third nm over v. Okay. The next part is, it says the mass of 1 mole of carbon dioxide is 44.01 grams per mole. It wants us to use the graph to calculate the number of carbon dioxide molecules in the container. So this here is telling us the mass of 1 mole. We obviously have to find the mass of one molecule, because from this equation, the small m, which we have in our gradient as well, is the mass of one molecule. So to do that, you have to do the mass of one molecule is equal to the mass of 1 mole divided by the number of molecules in 1 mole. We know the number of molecules in 1 mole is that constant 6.02 times 10 to the power of 23. So they've given us the mass, and we're just going to divide that by the number of molecules in 1 mole, and we'll get 7.31 times 10 to the minus 23 grams. Now because we're going to be using this and substituting in this value into our gradient equation, we have to change the grams into kilograms. So to do that, we're going to have to times 10 to the minus 3 again. So this minus 23 is going to actually become minus 26. So 7.31 times 10 to the minus 26 kilograms. So that is our small m. We want to find capital N. So if our gradient is equal to a third nm over v, we have, or we can calculate our gradient from our graph. We have m, we want to find this, and we are giving v. Now v at the top of the page is in centimeters cubed. However, we know that volume is usually measured in meters cubed. So to change it from centimeters cubed to meters cubed, I'm just going to multiply it by 10 to the minus 6. Okay, so that will become 50 times 10 to the minus 6 meters cubed. So looking at this, I'm just going to rearrange this equation to have n is equal to the gradient multiplied by v. I'm just doing it over here because I don't want to remember. Divided by a third times m. Okay. Now obviously I have to find the gradient. So from my graph, you try to draw your biggest triangle possible, and your gradient is going to be your change in y divided by your change in x. So you can pick your own numbers. I'm just going to write down the ones that I have marked out. My change in y is going to be 3,280 take away What was the other value? 2,400. Okay, so I've just taken away this value from this value. Divide that by my change in x, which is 1340, take away 980. And when I type that into the calculator, I get a gradient of about 2.4. Okay, so going back down to here, to find the number of molecules, I have to do my gradient times my volume. So I have both these, and I also have the mass of one molecule. So now I can just substitute in my numbers to get my number of molecules. So I'm going to do 2.4 times my V, which we said was 50, times 10 to the minus 6. Divide that by 1/3 times m, the mass of one molecule, which we found to be 7.31, times 10 to the minus 26. And when we do that, we get let's see, applied. We get a value of 4.9, which I'm going to change to 5. Round that up. 5 times 10 to the power of 21. Okay, and that is, sorry, my writing's horrible. That is the answer. 5 times 10 to the power of 21 molecules.